So then we can look at some properties of the Z transform. And again, all of these properties we already talked about multiple times, right? So all these properties we talked about for continuous time transforms, for discrete time Fourier transforms, for Laplace transforms, and now for Z transforms, okay? Everything is the same. So we have things like linearity, time shifting, scaling in the Z domain, time reversal, and so on and so forth, okay? So again, the only thing for Z transform, right, for when you look at these different properties, the only thing that you might want to pay a little bit more attention to is the resulting region of convergence, okay? So similar to Laplace transforms, right? For example, if you're looking at linearity, you may start out with region of convergence R1 and R2 for these two terms. But when you add them together, right, when you add them together, you know that the region of convergence should at least be the intersection of the two, okay? But it potentially can be larger because when you add them together, it's possible that the addition cancels out some poles, okay, some existing poles, and that will allow your ROC to be larger, okay? All right. So I don't want to go through these one by one, okay, because these are all the same. Maybe I'll talk about one that's a little bit different, okay? So this is linearity, this is time shifting, right? When you shift in time, this corresponds to this, you can think of it as a phase shift in the frequency domain, right? So in the Z domain, this is Z to the minus N naught, okay? So something similar occurs the other way around, right? And the time reversal, okay? So maybe this one is a little bit different, okay? So this is time expansion. So if you recall in discrete time, we cannot compress and expand the signal arbitrarily, okay? Because in discrete time, the indices must be integers, okay? So the only, related procedure that we can do is this time expansion, okay? So in time expansion, if you recall, we define this signal x sub k of n, which takes on the value x of n over k when n is a multiple of k and 0 otherwise. So what this does is basically takes the original signal x of n and inserts k minus 1 zeros in between every two samples. Okay, so you're sort of stretching this discrete time signal by inserting k minus 1 zeros in between. Okay? So what this does is inserts k minus 1 zeros in between samples. Okay? So in this case, the Z transform will be equal to x of z to the power k, and the ROC would be r to the power 1 over k. Okay. So you can derive this directly, actually. So by the definition of Fourier transform, a Z transform, you take the summation of xkn times z to the minus n. Okay. Now this signal is non-zero only for n that is a multiple of k. So I am actually just summing over n that are multiples of k. Okay. And for those values, x of k of n is xn over k. Okay, times z to the minus n. Okay. Now let me do a change of variable where I set m equal to n over k, so that I'm summing over m from minus infinity to infinity x of m times z to the minus mk, or k times m. Okay? And this you can view as z to the power k to the power minus m. Okay? So if you look at this, this is basically the definition of the z transform at the point z to the power k. Okay? So this is, by definition, x of z to the power k. Okay. So in this case, if you say that z is in the ROC of xz, okay? If you say that you have a point z that is in the ROC of this original transform x of z, okay, then you can infer that z to the 1 over k is in the ROC of x of z to the power k. Okay? So if z is in the ROC of x of z, meaning that if you plug in z into x, x of z gives you a finite value, right? It converges. So if this is true, then this means that if you plug in z to the power 1 over k inside here, you also get x of z, which is known to be a finite value. Okay? So this is why the ROC of this transform here includes all the values in the original ROC, but to the power 1 over k. Okay? Okay? So the other two, like conjugation and convolution, are also the same. So I don't want to go through them again. Okay? So this is conjugation, and this is convolution. Okay? So they are exactly the same as the case for Laplace transform. Okay? So this convolution is, as you know, is very important because this is going to be used to help you analyze linear time invariant systems. Okay? Because when you pass a signal, right, suppose you pass a signal x of n through a linear time invariant system with impulse response h of n, then what you get at the output is the convolution of the two. So then you can analyze this system in the z domain by taking the multiplication of the z transform of their respective z transforms, okay, which is much easier to do compared to taking the convolution. Okay. So we can look at this simple example here. Okay, so here suppose the impulse response is just the summation of these two delta functions. Okay. So in this case, we know that the z transform of this is just 1 minus z to the minus 1. Okay? So the z transform of delta is just 1, and the z transform of a delay of delta delayed by 1 is just z to the minus 1. Okay? So this is h of z. Okay? And the ROC is the entire z-plane except z equal to 0. Okay? Because if z is equal to 0, then this blows up and becomes unbounded. Okay. So by the convolution property, the z transform of the output y of z should be h of z times x of z, and this is just 1 minus z inverse times x of z. Okay? And then you can take the inverse z transform. So you basically have x of z, which translates back to the original signal xn. Okay. And you have z inverse times x of z. And this corresponds to a time shifting, okay? A shifting in time. All right, so this, if you multiply by z to the minus 1, this corresponds to shifting by 1 time index. Okay, so you have, in the second term, x of n minus 1. Okay. And then this example is also similar, right? So suppose you take the convolution between a unit step function and x of n, then its its z transform is just the product of their respective z transforms. And for u of n, the z transform is just 1 over 1 minus z inverse. Okay, so this is by example 10.1. Okay, times x of z. Okay. And the region of convergence should be at least the intersection of the region of convergence of the two. Okay, so ROC is at least the intersection of R. Suppose that R is the ROC of xn. It should be the intersection of R and the ROC of un, which corresponds to the value of z with magnitude greater than 1. Okay. Okay. All right, so these properties are the same as before, right? It's the same for Fourier transforms, continuous time Fourier transform, the same for discrete time Fourier transform, the same for Laplace transforms, and now also the same for Z transforms. Okay. All right. Now there are some remaining properties that also are the same. Right? This is the differentiation in the Z domain. And also similar to the Laplace transform, we have this initial value theorem. Okay. Right. So the examples are also the same as before, so you can easily look at them. But I guess what's more interesting probably is to look at the characterization of linear time invariant systems. Okay, so as I mentioned before, the key application for this is the convolution property. Okay, is the convolution property. Okay. Now, other than utilizing the convolution property to help you find the input and output relation, right? What's more interesting here is that by obtaining or by observing the Z transform of the impulse response, which we call either the system function or the transfer function. So this terminology is the same as in Laplace transforms. Okay. We can observe if the system is causal or non-causal, and we can also observe if the system is stable or unstable. Okay. So these statements are also the same as Laplace transforms, but there's a slight difference at the end. Okay. So for causality, this statement says that a linear time invariant system, discrete linear time invariant system is causal. Okay, is causal. What do we mean by causal? Right, causal means that Hn is 0 for all n less than 0. Right? Okay. So this says that the linear time invariant system is causal if and only if is a two-directional statement, right? If and only if the region of convergence is the exterior of a circle, including infinity. Okay. So if you recall in Laplace transforms, this is only a one-sided statement. Okay. So in Laplace transform, we only were able to say that if a system is causal, the ROC is the right half plane. Okay? But if the ROC is the right half plane, we cannot directly say that the system is causal. Okay? But why can we make this two-directional statement here? Right? So here we're saying that if your system has ROC that is the exterior of a circle, then it must be causal. Okay. So the key difference here is this last sentence. Right? So if you, in general, if you only say that the system function has ROC that is the exterior of a circle, you cannot guarantee that it is causal. You can only say that it is a right-sided sequence. So the reason you can say it's causal is because this ROC includes infinity. Okay? So why is that? Right. So suppose that you look at a general right-sided signal. Okay? The Z transform would be something like this. Okay. So when is infinity not in the ROC for this? Okay. So the infinity is not in the ROC for this when n1 is negative. Right? When n1 is negative, this means that you have a Z term with a positive exponent, so that when Z goes to infinity, this becomes unbounded. Okay? But if the system is causal, this means that n1 is greater or equal to 0. Right? So n1 is greater or equal to 0 for causal systems. And if n1 is greater or equal to 0, there is no Z term with a positive exponent. so that infinity can be included in the ROC. Okay? So the key for this, two-sided argument is this inclusion of infinity in the ROC. Okay? Okay? So, yeah, I think this is the only part that's different from the Laplace transform. Now, similar to the Laplace transform, we can also single out the case where the system is rational, okay? But we don't say much more in this case by having it being rational, okay? Because we already are able to get a two-sided argument here. So in Laplace transform, in order to get the reverse argument, you need the system to be rational. But in this case, you just need infinity to be in the ROC. Okay. Now, if you single out the case where x of z is where h of z is rational, what else? What more do you get? Okay. So the only thing you get, in addition to what we already have, is that this circle must be outside the outermost pole. Okay. All the other arguments are more or less the same. Okay. So this is saying that this system, if it is rational, okay, this system is rational if and only if the ROC is the exterior of a circle outside the outermost pole, okay, and when you express h of z as the ratio of two polynomials, the numerator, the order of the numerator polynomial cannot be greater than that of the denominator polynomial, okay? And this statement is actually the same as this statement, okay? Because if you have a numerator polynomial that has degree larger than the denominator polynomial, right? The order of z in the numerator is larger than the order of z in the denominator. Then as z goes to infinity, this thing blows up, right? So if you have a numerator degree or order of numerator larger than order of denominator, then infinity will not be in the ROC. Okay? So in order for infinity to be in the ROC, this ratio, this statement here must hold. Okay? So for me, this is basically saying that infinity is in the ROC. Okay? So nothing more is really said by having h being rational. I think the only additional thing is just that it should be outside of the outermost pole. Okay. Okay. Right. So the last thing would be the stability. Okay. So the last thing would be the stability. So this part is more or less the same. Okay. So you say that an LTI system is stable if and only if its ROC, okay, includes the unit circle. And this is because if it includes the unit circle, then the Fourier transform exists and the impulse response is absolutely summable, right? Because in this case, Fourier transform exists and therefore Hn is absolutely summable. So suppose you look at this example here. Okay. So for this example, you actually have two poles, one at 1/2 and the other at 2. Okay. Now, if you say that the region of convergence is greater than 2, then obviously it does not include the unit circle. Right? So suppose that this is the unit circle. Then if you say, so this is 1, this is 2. Right? So if you say that the region of convergence is this, then it does not include the unit circle. And therefore, the system is not stable. Okay? Okay. So here we have two poles, right? One at 1/2 and one at 2. So there are three possibilities of the region of convergence, either inside 1/2, outside 2, or the ring in between 1/2 and 2. And only this case will you have a stable system. Okay? So only when the region of convergence is this ring here, okay? Only if the ROC is this ring here. Okay. So when it is this ring, then this means that if it is this ring here, then this means that this is a right-sided signal, but this is a left-sided signal. Okay. So in this case, the impulse response should correspond to 1/2 to the power n un minus 2 to the power n u of minus n minus 1. Okay? So when it is right-sided, this follows from example 10.1. If it is left-sided, it follows from example 10.2. Okay? Okay. So if you recall, in Laplace transform, we mentioned that if you have a causal system, then the system is stable. If you have a rational causal system, then the system is stable only if your poles are in a negative plane. Okay? Because the region of convergence must be to the right of the rightmost pole. So all of your poles must be on this side of the plane. Okay. Now, similarly for this Z transform as well, if your system is rational and causal, then your region of convergence must be outside the circle corresponding to the outermost pole. So if you want your system to be stable, your outermost pole must be inside the unit circle. Okay. Whenever you have a pole that is outside the unit circle, this causal system cannot be stable. Okay. So this is the statement given here. Right. So a causal linear time invariant system with rational function. Okay. So for something that is causal rational, it is stable if and only if all of the poles lie inside the unit circle. Okay? Okay. So this is this is a simple example, right? So for this example, the pole, you have a pole at A, right? So if the system is causal, then this must be right-sided. This must be right-sided, meaning that the region of convergence is outside of the circle corresponding to A. So if you want the system to be stable, A must be less than 1. Okay. So in this case, the system is stable only if A is less than 1. Okay. So let me do one last example. Okay. So through these discussions, like in the Laplace transform, we talk a lot about cases where H are, the transfer functions are rational. Okay. So then you may wonder, when do we get a system function that is rational? Okay. So in the continuous time case, we get system functions that are rational when we have a system described by linear constant coefficient differential equations. Okay? So in discrete time, differential equations correspond to difference equations. Okay? So this is just another example of including or not including the unit circle. Okay? Okay. So here is an example of linear time invariant systems described by difference equations. So the treatment here is the same as continuous time. To get the system function, you do the z transform on both sides. So this will give you y of z minus 1/2 z to the minus 1 y of z, because a time shift corresponds to a multiplication of z to the minus the amount of the shift. Okay? And on the right-hand side, we have x of z plus 1/3 z minus 1 times x of z. Okay. So just by rearranging the terms, right, dividing x of z to the other side, okay, you get h of z, which is y of z over x of z. And this is 1 plus 1/3, the inverse 1 minus 1/2, the inverse. Okay? Or you can write it in terms of the polynomial of z. So if you multiply z in both the numerator and denominator, you get z plus 1/3 and z minus 1/2. Okay? So in this case, you have a 0 at minus 1/3 and a pole at 1/2. Right? So if you plot this out, you have a 0. Suppose that this is the unit circle. Okay, so suppose that this is 1. So you have a pole at 1/2 and a 0 at 1/3. Okay. So this is the system function that you get from a system described by difference equation. Okay. And you see that it is in a rational form. So as in the continuous time case, this extends to arbitrary number of terms as well. Okay? Now, when you get a system function like this, right, you see that it has a pole at 1/2. So there are only two possibilities for the region of convergence. Okay? One is that it must be outside of the circle with radius 1/2. The other is that it is inside the circle of radius 1/2. Okay? Okay. So suppose that the system is causal, right? Then it would be outside this 1/2. Okay. So if system is causal, then the ROC corresponds to z greater than 1/2. And if the ROC is z greater than 1/2, it would include the unit circle, and therefore the system is stable. Okay? Now, on the other hand, if you have a region of convergence that is this inner circle, then the system would not be stable. Okay? And in fact, the system is also not causal. Okay. Okay. All right. So that's all I want to talk about for this chapter. But the main point here is that you can do the same thing as the Laplace transform for continuous time signals. You can do the same treatment for discrete time signals using the Z transform. Okay. So if you compare all the examples in the two chapters, you will see that they basically are one to one corresponding to each other, right? So we also have this example for continuous time as well. Okay, and the reason is because all the concepts extend to the other side. Okay, so in discrete time, I would say the only thing that is different is how you visualize the region of convergence. So instead of having region of convergence that is either the left hand side or the right half plane, right? Left half or right half plane, you now have the exterior of the circle corresponding to the right half plane and the interior of a circle corresponding to the left half plane. Okay, everything else is more or less the same.